Yeah. Hello students. So in this session we are going to discuss an overview of the chapter chemical kinetics, especially on the order and molecularity of a reaction, right? So we'll also touch about the half-life of a reaction. Okay, so basically in order to start, what is a chemical kinetics? So kinetics refers to rate of a reaction. Which reaction? It is a chemical reaction. Rate of a chemical reaction. Assume that you have a reaction where A is converted to B. Means a reactant A is converted to product B. As the reaction progresses, what happens? As the reaction progresses, concentration of A decreases, whereas concentration of B increases. Right? Now, this concentration of A can decrease instantaneously or at a slower rates. So we want to know what is the rate of this reaction. What is this rate of the reaction where a reactant is converted to product? So rate of a reaction, usually we calculate the concentration of a reactant upon time. So what is this concentration? Concentration of a reactant. So what is its initial concentration and how the initial concentration is affected as the reaction progresses, right? At what time the whole concentration is reduced. Okay, so this is what we are going to. So we have different order of reactions, say zero order, first order, second order, third order. So we need to determine the order of a reaction also. Now I can say rate of a reaction is equals to concentration upon time. We can also plot a graph wherein which I can say this is a time and here we have a rate. What happens? Initially assume that the concentration is here, the A. As the time progresses, it keeps reducing and at a certain point the whole concentration of A is converted to B, right? So this is what. In the same graph, if you have to plot against the reactants, right, I can plot in this way, wherein which it's look like this. So what happens? This is for the product. That means as the reaction progresses, the concentration of the product increases, and as the reaction progresses, the concentration of reactants decreases, right? Now if I say rate, simply change in concentration upon time. This can be either plus or minus. Minus indicates the concentration is reducing. Minus indicates the concentration is reducing or decreasing. Now, for example, look at this reaction. AA plus BB gives rise to CC plus DD. So what happens here? Rate, for example, if I say rate of disappearance of A, rate of disappearance of A equals to minus dA by dt, because A is your reactant. So as the reaction progresses, the concentration of A decreases. So we have to say rate of disappearance. So as the concentration is decreasing, that's the reason why we are using the negative symbol here. This implies that the concentration is decreasing. In the same way, if you want to say for with respect to C, I can say rate of appearance, because product is not present until the reaction starts. So I can say the product is appearing. So I can say rate of appearance of C equals to, this will be plus dC by dt. That means I can say rate of disappearance of A, or I'll write on the same thing here, Cc plus dd. Here rate of disappearance, what we are calculating, rate of appearance or rate of formation of C and D. So what is the rate of reaction? It's simply the concentration upon time. So I can say this delta can be replaced. For example, with respect to D, rate of formation of D, this is D concentration by change in time, like this. Got it? Okay, let us look into this. Remember the units. I'll come to that, what is exactly the zero order, first order, second order and all. But if you see zero order kinetics, which means it will be K, which is rate equals to concentration time inverse, right? So rate of reaction, which is a zero order, which follows a zero order. I'll explain you how to find out the order of a reaction. Okay, but initially you just remember this. If I say first order kinetics, first order kinetics means a rate of reaction is depend upon the concentration of only one reactant. See, as you have seen in SN1 reaction, right? So what exactly happens in the SN1 reaction? You have a alkyl halide. So this alkyl halide is converted in the presence of a nucleophile, is converted to a substituted nucleophilic product. Okay, then this. But in the slow step, there is involvement of only alkyl halide. That means the rate of reaction is depend upon the concentration of alkyl halide that is present. Means though there are two reactants involved in this reaction, if the concentration of the if the rate of reaction is depend upon the concentration of only one reactant, then I can say this is a first order reaction or first order kinetics. Second order kinetics, very simple again. It is a SN2 reaction where the rate of reaction is depend upon the concentration of two reactants. So in first order kinetics, if you look at the rate of a reaction, that is K equals to rate by, this is sorry, rate constant equals to rate of the reaction upon concentration of one reactant. So the units for rate of the reaction is concentration time, whereas for concentration of A is only concentration. So as you know, this gives you time inverse. That means rate constant for a first order reaction or first order kinetics, the units will be time inverse. Same way for second order kinetics, what's going to happen here? Rate constant K equals to rate of a reaction by concentration of two reactants. Means rate of the reaction, you know, that is concentration by concentration. That means concentration of A and concentration of B. Into time inverse. So here concentration inverse and time inverse. That means this is the units for second order kinetics. The same way you can proceed further like for third order kinetics, where in which we can say K equals to rate of a reaction by concentration of three reactants. I can say here it will be concentration into time upon concentration of A, concentration of B and concentration of C. Upon elimination there is concentration to -2 and time -1. So what exactly the units for the concentration? We can say it is mole per liter or mole per cubic decimeter. In the same way for time it can be second inverse or minute inverse, sometimes even hour inverse or even day also. This can be for time. This will be for concentration. That means if you have to write down for second order kinetics the units, then it will be like mole per cubic decimeter, then second inverse, for example. So this will be the units. Then okay, you understood something about unit. Then how to find out the order of a reaction when the experiment is given? See, order of a reaction can be found out experimentally. Theoretically it cannot be found out. Okay, you can predict the order of a reaction only through carrying out the experiments. So theoretically can be found out means yes, provided if you have an experimental data with you. How? We'll see. For example, let's say okay, we'll find out the order of a reaction. Here I can say the reaction nitric oxide with chlorine gives nitrosyl chloride. So I'm providing you the experimental data here. Let's say this is I'm trying out with the different trials, okay, where this is the concentration of nitric oxide and I have the concentration of chlorine here, I have the concentration of the product. Okay, so initial rates, initial rate of the reaction, I can say initial rate of the reaction. Say in the first experiment I have 0.250 concentration, that is mole per cubic decimeter. You can say mole cubic decimeter. Here also I can say mole cubic decimeter. This is the rate or rate constant, that is mole cubic decimeter second inverse, initial rates. Now this is 0.250. Here I can say 0.250. Here 1.43 into 10 raised to -6. In the second trial where I have the concentration of the nitric oxide is kept constant but the chlorine is doubled. Here say I have like this. The third experiment I have doubled the concentration of nitric oxide, say it is here, I kept it as constant. Now what I'm seeing here 1.44 into 10 raised to -6. So by this, so I have given you the 3 trials here. What can you predict here? Look at the first experiment where if the concentration of nitric oxide and concentration of chlorine is taken as 0.25 mole per cubic decimeter, the rate of the reaction is found to be 1.43 into 10 raised to -6. Okay, Now let's see whether the reaction is dependent. See, this is the concentration what I have taken initially. So initial concentration doesn't matter for me. When it matters, when I go to the next experiment where I'm keeping the concentration of nitric oxide constant, but I'm varying the chlorine concentration, which is doubled. I found out this is also doubled. If I'm increasing the concentration of chlorine is doubled from 0.25 to 0.5, I found it here 1.542 to 2.86. That means if I'm doubling this concentration, the rate of the reaction is doubled. That means this is directly proportional to the concentration of chlorine. But how many times, we'll see. But this is dependent. Now we want to see whether the initial rate of the reaction is dependent upon the nitric oxide or not also. Okay, what I have done, I just kept this as constant now, right? Chlorine concentration is kept constant. Now the concentration of nitric oxide is doubled. So whether it has changed 1.2.86, right, or not, means you can see here when I have doubled the concentration, this is reduced, right? Okay. So I just want to see, that means if I'm increasing the concentration of 0.250 to 0.50, okay, ignoring this, the concentration is slightly affected. 1.43 here, 1.44 here. Sorry, this is 11.44 here. It is affected. So what does this mean? Which means if I say for this concentration of nitric oxide is, say, trial 3 by trial 1, which is 0.250. So here, say I'll take this value as x, and here it is 11.44 into 10 raised to minus 6 upon, okay, say this is y, right? This is x and this is y. Now what is happening? This is 2 power x, which is 1.43. This is by this gives you 8. Now make the bases equal. 2 power x is 2 power 3. When the bases are equal, then exponents x equals to 3. Means the rate of the reaction, that means this is a third order. 3 times. Means if I'm doubling the concentration, the rate is increased by 3 times. This is third order kinetics. That means the rate of the reaction on nitric oxide is a third order. Then with respect to chlorine, what is happening? Just have a look at this here. With respect to chlorine, say trial, I can take this one and this one, because this we have kept constant. We have changed, we have affected the nitric oxide concentration. So let's say trial 2 by trial 1, which means it is 2.86 by 1.43, right? Here it is again 2 here. So 2 power x is 2 power 1, where x equals to 1. Means this is a first order kinetics. Means concentration of chlorine is first order, whereas the concentration of nitric oxide follows third order. So overall reaction is the 3 plus 1. This is the 4 order reaction. Let us look into another data here, where I'll show you the reaction 2ClO2 plus 2OH minus. This gives rise to chlorate plus chlorite plus water. So we want to see the concentration, that means whether the rate of the reaction is affected or is depend upon the which reactant or both the reactants. Okay, let's look into the experimental data here. So these are the trial 1, trial 2, whatever. Here I have the concentration of chloride, here the concentration of OH minus, then it is the initial rate of reaction. Okay, if I say the trial 1, let's take this as 0.012 moles and this one as 0.012 moles, and the initial rate should be 2.07 into 10 raised to minus 4 moles per second. So here also let's say 0.024, 0.012, 8.28. Okay, let's complete the question here. Then I'll take the data 0.012 molar, 4.14. Okay, and trial 4 will be 0.024. So here 1.66 into 10 raised to minus 4. Okay, now this is your question. Try to understand the question first. Okay, so you have the 4 trials here, the concentrations were given. Then what is happening? 0.012 and 0.012, where you have 2.07. Say this is as the first experiment. Okay, now let's see, keep the concentration of OH minus constant, double the concentration of ClO2. What is happening? Look at this. Yes, there is drastical change, right? From 2 it is increased to 8. Means the rate of reaction is depend upon the ClO2, but how many times we need to predict it. Here also in the next one, if you look at the trial 2, it is only for ClO2 concentration. Look at the trial 3, where we kept the concentration. See, every time you need to compare with the trial 1. How much deviation is there from the trial 1? Okay, so trial 3, we kept the concentration of ClO2 constant, but the concentration of the OH minus is doubled, 0.024. So what happened to the concentration? Yes, there is change in the concentration, which means the rate of reaction is directly proportional to both the reactants. But how many times we'll see here? Okay, here what is happening? If I'm doubling the concentration in both the cases, there is really a very good increase. Here 1.6 is 10 power minus 3. There is a very good increase in the rate of the reaction. Okay, so how do you find out? Let's say here for ClO2, I'll take up trial 2 over trial 1, which means 0.024 upon 0.12 to power of x equals to 8.28 into this will be like this. So here, which means 2 power x is equal to almost 2.07, and this will be 4, or I can say 2 power x equals to 2 power 2. I can say x equals to 2, which is a second order kinetics. Whereas for OH minus, let's say trial 3 by trial 1, which is 0.012, that is equals to 4.14, right? So this will be 2 power x, so this can be like this, 2 power x equals to 2, right? So x equals to 1. So this will be going to a first order kinetics. So overall order of the reaction will be 2 plus 1, that is the third order kinetics. Okay, let's find out the value of k here. Okay, I'll just put it here for you. Determine k using data present in experiment 1. So how do you say? This is your first experiment, right? From this I can say, so what is the formula for this one? Let's write down. Rate equals to K into concentration of ClO2 and concentration of OH minus. I'll say the concentration of here X and concentration of here Y. Now, okay, so the K value is given for this. Based upon this one, I can say 2.07 into 10 raised to minus 4 moles per second is equals to K into concentration of ClO2. So concentration of ClO2 here is 0.012 and Y is 0.012 again. But what is the X here? X is depend upon 2 times here. This is 2 times, this is 1 time. So I can say 2.07 into 10 raised to minus 4 K into 0.012 3 times. Got it? K equals to, so this is molar cube. Okay, I can say 2.07 into 10 raised to minus 4 by 0.012 mole cube, or K equals to 2.07 into 10 raised to minus 4 moles per second by 1.7 into 10 raised to minus 6. This. So just calculate, you'll get the value of K. So this calculates, so the value or the units will be m minus 2 s minus 1. This is the units for the rate constant. So m minus 2 s minus 1 means this is represents third order kinetics. This represents the third order kinetics. So this is how you can calculate the K value from the given experimental data. Okay, so let's say half-life. Half-life for first order especially, that means how much of the reaction, like I can say T half, where time taken for half of the reaction to complete. T represents time. So for the first order kinetics, the T half is 0.693 by K. Do you know the value of K? Yes. K equals to, here 2.07, so I'll get the value as 120 molar minus 2 s minus 1. That means, what exactly I'm trying to say? So from the order of reaction, you are predicting the order of reaction. From the order of reaction, we are extrapolating the data to find out the rate constant. Once you found out the rate constant, you can just extrapolate the same thing. For example, I'm showing the T half or half-life for the first order kinetics. First order kinetics, that is T half equals to 0.693 by K. Okay, that means if you just substitute the value of the K over here, you will get the value. Right? For example, assume that the half-life of radon is 3.8 days. After how many days will 1/20th of radon sample be left over. So we can say here simply lambda equals to, based upon the first order kinetics, lambda equals to 0.693 by t half, right? So what is the t half here? So 0.693 by 3.8. Okay, so this gives you the value. Now if I say the same thing, extrapolate it to, say, let the initial amount of this, write down, be n0. So after the specific period of time, it will become n. So, and amount left after t days, be n. So this is equal to, or which is equal to n0 by 20. Got it? Because you can see here 1/20th n0 by 20. This is what? T equals to 2.303 by lambda log n0 by n. Same thing, 2.303 by 0.182. So this value log to the base 10. Here n becomes n by 20. So this is how you need to calculate. So this becomes again log 20 to the base 10, log 10, this, right? So find out the log 20 value, substitute here, you will get the value, and the units will be in days. How many days, right? So this is one kind of questions what you can expect, finding out the half-life. Now can you tell me what is the molecularity of a reaction? If you have a reaction that is happening in a single step, okay, we call usually as elementary reaction. Whereas if you have a reactions where you have where there is involvement of one molecule, we call it as a unimolecular, two molecules is a bimolecular, then three molecules is a trimolecular. So this represents the trimolecular reaction. For example, see this. So molecularity of a reaction. PCl5 gives rise to PCl3 plus Cl2. Here the reaction, whole reaction is dependent upon the one molecule. I can say this reaction is a unimolecular reaction. Okay, there is only presence of one molecule here. And these reactions, very simple reactions, are called as elementary reactions. In same way, H2 plus I2 gives 2HI. There are two molecules that are involved. One is hydrogen and is iodine. So this is a bimolecular reaction, right? So number of molecules involved, that gives you the molecularity of a reaction. Whereas order of the reaction is quite different from that of the molecularity. So you need to understand what is the basic difference between the order of a reaction and a molecular reaction. Order of reaction we have seen. Okay, so how to predict the order of a reaction and how you can find out the rate constant also along with the units. Whereas the molecularity of the reaction is the number of molecules that are participating in the given reaction. So this is all about chemical kinetics, students. Thank you.